Hello everybody, welcome to the Institute. In this little set of problems, on the latest set they're 13 and 14, but sometimes they've been other numbers. They involve friction being the only thing bringing something to a stop. So like in problem number 13, we've got the car is taking out a gear, so it's friction that's going to bring it to a stop, and then in 14 we have a tennis ball. I'm going to kind of show an extra little tidbit that's kind of neat about this and kind of develop another equation. And I'll put this equation up on the equation wall eventually. So when I think of, I'm just going to use either one of these. If I draw a free body diagram, we have three forces acting on the object. We obviously have the force of gravity. We've been mentioning that over and over again. And that's going to be equal to m times the acceleration of gravity, so mass times gravity, or m times 9.8. And then we'd have the normal force. Now, since neither one of these is going to be moving up and down, these two would actually have the same magnitude. So the normal force would also equal m times g. At least that would be its magnitude. The other force that we have here, and I'm going to change the color just so we can kind of see it, would be friction. In both of these, this one we're kind of talking about rolling friction, this one we talk about kinetic friction, but they're both basically kinetic friction, so I'll just write it as Fk. So when we're trying to figure this out, in 14 we actually have something about the coefficient. In 13 we're trying to find that coefficient. So I'm going to kind of show you an easy method of going about that. In both situations, we know we have a net force that's going to cause some kind of acceleration. And this is going to be like a horizontal acceleration. Well, the net force in both of these problems is just going to be friction. It's the only things bringing it down. But since the object, and I'm going to change this color, since the object is actually moving to the right, so this is a velocity to the right, but it's slowing down, I'm going to treat this as like a positive, so my friction is actually going to be negative. So when I put this in, I'm going to write it as minus Fk equals m times a. Now the reason why I'm doing this is I'm going to actually create a new equation just to kind of help us out a little bit. Since the friction force is equal to the normal force multiplied by your coefficient of friction, I'm going to replace this part with minus, I've got mu k times my normal force, and that would equal m times a. But in our situation, our normal force just has a magnitude equal to the weight of the object. So I've done this before where I replace this Fn in here with this mu k, m times g. I've done the silly stuff that, friction could be, if I move the letters around, it could be mug, it could be gum. If I move them to, the letters to different places. But that's kind of irrelevant right now. The reason why I'm doing this is now what you can see is that the masses are going to cancel, and I come up with this neat little equation that the acceleration of something, and this is only the acceleration when friction is the same thing slowing it down, is equal to minus, because it's slowing down, mu k, it's going to be kinetic friction, times the acceleration of gravity. And this is the new equation I can use in both of these problems. So then when I come up here and I say, okay, how do I solve this one? I'm trying to find the coefficient of friction. Well, I'm going to find that coefficient of friction. It would equal, I'm just going to rearrange this equation, it would equal minus the acceleration over gravity. So I've got gravity, I know that's 9.8, I just got to figure out the acceleration. So then I look up here and I go, oh, I've got a time, I've got an initial velocity, I've got a final velocity. I should be able to find my acceleration from Vf minus Vi over t. Now the only extra thing to watch out for on this one is don't forget these are in kilometers per hour. We've got to change those into meters per second. Easy way to do that is divide by 3.6. So if I divide by 3.6, that'll change those into meters per second for us. So that's a neat little method. So I'm using this new equation to actually find a relationship between acceleration and the coefficient. And in problem number 13, we find the acceleration first, and then we can plug it in here to find my coefficient. In 14, we're going to do the opposite. We have an initial velocity, and it's going to roll to a stop. We're trying to find the time. So we'll start out with this equation, and then once I have that acceleration, I can actually plug it in to this equation. But if I rearrange it, if I take my t and my a and have them switch places, time would equal the change in velocity over my acceleration, and then I can find my time that way. Notice in problem number 13, they gave us the mass, but the mass actually cancels, so we don't need it. And in 14, they didn't give us the mass, so we didn't need it. So just wanted to kind of point that out. So a little bit of help on these two problems. Hope you enjoyed this edition of the Henstitute.